Any questions about anything?
It's not hard to show that there's a strategy, you know, 2-1, no 2-2, 3-2, and then 3-3.
Where's Gabriella? She was here a minute ago. Oh, okay, okay. Any questions? Just a couple of reminders. Homework 4 is due today. Unless you've been in touch with me because of illness or something like that and you made a special arrangement. Homework 5 is due next Tuesday. And homework 6, there's 3 problems that I asked you to do. And and you can hand them in anytime up to like midday Monday before the final because I want to post solutions that day. Final exam is, by the way, is Tuesday the 13th in the evening. So you have like a whole day of, you know, thank goodness we have it at a civilized time and it's in the most comfortable room, the engineering quad, Phillips 101. There's more leg room there than any other lecture hall on campus as far as I know. And also, I put up a handout the other day on the evolutionarily stable strategy concept. I put up a handout this morning on the replicator dynamics, which we just started talking about. And there's going to be one more handout on the replicator dynamics for scissors, paper, rock, which I'm going to talk about some in class, but there's going to be more details in that handout. Okay? So any questions about that stuff or anything else before we move on? All right. So remember what we were doing at the end of class last time. We finished talking about the evolutionarily stable strategy stuff, and we started talking about this thing called the replicator dynamics. And this was due originally to Taylor and Yonker in the late 70s. And this is one of several approaches to what I call the deterministic dynamical analysis of evolutionary game theory problems. And the operative word there is dynamical. The evolutionarily stable strategy concept was static in some sense. There was no accounting for, say, how an invading strategy might appear in the population. There was no accounting for how an invading strategy might either get wiped out or overrun the population. Replicator dynamics takes care of part of that problem, part of that missing stuff, but doesn't take care of the rest of it, as you'll see. And the handout has a lot of details, but I'm just going to cut to the chase in class. The setup is, once again, you have a finite symmetric game. That has action space A1 through AN. And this is a finite 2-player symmetric game that has action space A equals A1 through AN for each player. And payoff function U of AI, AJ equals the payoff to an AI player against an AJ player. Doesn't matter which player they are in the game. So this is the same starting point as the ESS stuff. And you have a population. And generally we consider this to be a large, perhaps finite, perhaps infinite. Both of those cases I deal with in the handout. Population of players. Each programmed or hardwired, or however you want to think of it, to play a pure strategy of the game. And so you can think of this population, they're not rational players at all. They're just, you can just think of it really as a multi-set of strategies, if you wish. So it's really just a multi-set. That's something we encountered when we talked about genetic algorithms of pure strategies. just floating around. So you can think of these things as maybe DNA strands or whatever. They're programmed to make some protein, and that's all they do. And the way that the population evolves, I talked about a little bit last time. And I'll just say more in the handout, but if we let p sub I equal to the fraction of p sub I of t be the fraction of the time t population programmed to play a sub I, and that's for all the i's, 1 through n, then a sort of quote-unquote payoff proportional cloning argument leads to the following difference equation governing how the population fractions of the various actions, various pure strategies at time t plus 1 emerge from those at time t. And those equations look like this. P sub I of t plus 1 is equal to u of a sub I p of t. I'll tell you what p of t is in a second. Divided by u of p of t times p sub I of t. And that's going to be for all i's. And that is one form of the discrete time replicator dynamics. It's not quite the standard form that you might see in the literature, but it behaves the same in all important ways. And I omitted saying something last time. I'll admit that I did not omit it on purpose, but what you have to do before you set this up to avoid dividing by 0 is, before you derive those equations, if necessary, you add a positive constant to all the payoffs in the game to make them strictly positive. And that's sort of analogous to assuming that the fitness function in a genetic algorithm was strictly positive. And this turns out not to matter. It doesn't change anything, really. It keeps the Nash equilibria of the game the same. It keeps the behavior of these dynamics the same, and except for modulo a little bit of things about how fast do they move and all that kind of thing. Everything does the same thing, maybe at a different speed. I don't want to worry about that detail in class because we just don't have enough time to sweat all that kind of stuff. Yeah. Oh, bless you. I thought you said professor. It has the same kind of structure to it. Yeah. Okay. All right. So what is P of t? P of t is just going to be the sum P1 of t, A1 plus P2 of t, A2 plus dot 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 plus Pn of t, A sub n. This is the notation we use if we have like P1, A1 plus P2, A2, and so on for a mixed strategy of the game. And this is the so-called population strategy. And I want to emphasize that in this setup, nobody is playing this strategy. Everybody's just playing a fixed pure strategy all the time. Although no one's playing it, the payoff to any agent in this population against a randomly chosen opponent, which is how we get this payoff proportional cloning argument, is the same as the payoff of that agent playing its action against this pure mixed strategy in the static game. So although nobody plays P of t, U of a sub I P of t is the payoff to an AI player against a randomly chosen opponent, which is where the the payoff proportional cloning argument comes from that I talked about last time. So if I'm in this population and I'm playing AI and I pick a random opponent and get my payoff, the expected value, and this is, I should really put expected in here, the expected value of the payoff I get is the same as it would be if I were actually playing the game against a rational player who was playing that mixed strategy. And that's why people call it the population strategy. Okay. Now there's a few salient things about this. And by the way, difference equations of this kind are perfect for like simulation. You know, it's really easy to write a little program that does this, and it turns out that the formulas for U of AI P of T and U of P of T P of T are always really simple. They're both linear in the entries in P. This one is actually linear, this one is actually bilinear in the entries of P of T. So they're really easy to, it's really easy to write up a program to simulate this thing, run it and see what happens, and it's kind of fun to do that. You know, you can do it in MATLAB or whatever. But the point is, these are really amenable to simulation. Okay. And here's some points things I want to point out in general before we look at our example games. Some things to note in general. Okay, what is the meaning of the numerator and what is the meaning of the denominator? So the numerator, U of AI P of T, is equal to the expected payoff of an AI player versus this population strategy P of T, which is the same as the payoff he or she or it would get against a randomly chosen opponent. U of P of T P of T is equal to the average of this over all agents in the population. And if you want to see why that's true, if you just expand P of T out as P1 of T A1 plus P2 of T A2, this comes out to be the sum from I equals 1 to n of Pi of T U of AI P of T. So all you're doing is taking U of AI P of T and computing its expected value over all the agents in the population. So what does that tell us? That tells us, notice that Pi of T plus 1 is the ratio of those two guys times Pi of T. So what happens? If AI is better than average against the population strategy, that means this quantity is bigger than this quantity, which means that Pi of T plus 1 is something bigger than 1 times Pi of T. In other words, Pi of T increases as long as it's not 0 from time t to time t plus 1 if AI is better than average against the population strategy. So if Pi of T is non-zero and AI is better or worse than average against P of T, then Pi of T plus 1 is bigger than, respectively less than, Pi of T. So above average strategies increase, below average strategies decrease. And this is a lot like what was happening sort of in genetic algorithms, except the thing that plays the role of the fitness function, the payoff here, is endogenous. It's endogenously determined. How good you are isn't from the outside. It isn't just some F that descends to the problem. It's determined by who else is in the population. Okay, so note, there's sort of no quote-unquote exogenous specification of quote-unquote how good AI is, it depends on, quote unquote, who else is there. Who else is around? That is to say, on P of t. And this is where this endogenous fitness idea really takes off from the exogenous fitness we saw in the genetic algorithms. That's one thing to note. Okay, now it's very important, this thing, if pi of t is not 0, then pi of t plus 1 is bigger than p of t. Because if pi of t is 0, what is pi of t plus 1? What if pi of t is 0? What is pi of t plus 1? 0, right, because pi of t plus 1 is thing times pi of t. And no matter what thing is, 0 begets 0. And that's an important point to note. So the second point is, if pi of t equals 0, then pi of t plus 1 equals 0. And we can sort of interpolate that back to the beginning. So in particular, if pi of 0 is 0, then pi of t is going to be 0 for all t. And in words, talking about populations, what this says is that if a given action, if a given pure strategy is not represented at the beginning, then it never appears. Okay? So thus, if AI is absent from the population, the initial population, AI never arises. And thus, replicator dynamics fails to take care of that second defect in the ESS, which was there's no way to explain how new things invade the population. Okay, so this is sort of a defect of the replicator dynamics, but which the other approaches to evolutionary game theory take care of. But it's important to note, important to remember. If a strategy is absent, it never appears. Okay. Third thing I want to recognize, when you're dealing with difference equations, those of you, I know there's at least one person in the class who's taking Strogatz's course on nonlinear dynamics, and yeah, there you are, and chaos. And so if someone comes up to you on Ho Plaza, right, and hands you a difference equation, what's the first thing you look for? That's not relevant to my question. No, that's only for linear things. This is nonlinear. Like if you have a difference equation, you want to analyze it mathematically, what's the first thing you look for? Okay, and then the next thing you look for? Yeah, that's the big question you want to answer, but okay. What's that, Andrew? Highest order term. Well, the terms aren't very high order here. It's linear here, quadratic here, quadratic denominator, linear numerator, you know. Anybody else want to hazard a guess? Okay. Okay. I guess I'm missing the target here. You look for fixed points. That's what you look for. That's the first thing you look for, is fixed points. What's the simplest thing that can happen in a difference equation? You can start somewhere and you can stay there forever, right? So what are the fixed points? So let's look at the fixed points of the replicator dynamics. And what do I mean by fixed points? I mean a population strategy, a distribution of fractions of players of the various pure strategies that stays the same from time t to time t plus 1. So let's adopt some notation for that. That is to say, a choice, or choices, because I said fixed points, p1 bar, p2 bar, dot, 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 pn bar of player fractions, or strategy fractions, such that if p of t is equal to this p bar, so pi of t equals pi bar for all I, pi of t plus 1 is also equal to pi bar for all I. That would be, in some sense, a stable distribution of strategies, right? And I'm not using stable in a technical sense because you could, if you understand anything about difference equations, you know that they can have stable and unstable fixed points. We'll have more to say about that in a moment. But this is the first thing that I usually look for when I'm presented with a difference equation on Ho Plaza or anywhere else. Okay? All right, so trivially, let's see if we can just think of our intuition about what's happening here. What are some trivial fixed points of the replicator dynamics under all circumstances? What kind of population distribution of actions obviously stays true? Exactly, and I'm sure that's what you guys were going to say as well. Over here. So trivially, every monomorphic population, and here we're meeting up again with these things that we made friends or enemies with when we talked about GAs, every monomorphic population, that is to say, every population that features only one of the AIs, so every population where everybody is playing a sub I for some fixed I and all the other a sub j's are 0. So with p j equals 0 for all other j is a fixed point. Of these replicator dynamics. And I think what I want to do is I'm going to write the replicator dynamics way over here and way over there just so I have them up and I don't have to keep rewriting them. So pi of t plus 1 is equal to u of ai p of t over u of p of t p of t times pi of t for all I. And the same holds true over here. Okay, so every one of those is trivially a fixed point of the replicator dynamics. Comment, Vincent. Why is this difference equation? Because you have pi's here and pi's here, so there's quadraticness going on here, and you've got quadraticness in the denominator as well. It turns out, actually, it's an interesting point occurs to me from your question. When people first came up with these models, they thought, oh, because of the special form of these dynamics, we ought to be able to say all kinds of cool things in general about them. Like no matter how big n is, blah, 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 blah. Because everything's all kind of bilinear-ish and special form. But it turns out you can get every complexity of nonlinear dynamics that you could dream of, chaos, whatever, strange attractors, all that stuff, from equations of this kind. So there's no sort of sledgehammery kind of general results you can prove despite the hope that you might have based on their special form. And that either makes you happy or it makes you sad. Or you don't care, I guess. That's possible too. Okay, so what's the commonsensical reason why a monomorphic population is fixed? Drew, you were the one who proposed the fixitude of those. So what's the commonsensical reason without talking about equations or ones and zeros or anything like that?
Because actions that aren't represented in the population will never arise, so you're never going to have any new actions coming forward.
Yeah, so if everybody starts out as AI, then everybody's going to be AI forever. Actions clone themselves. They don't give birth to other actions. Okay, so this is obviously true both from a commonsensical standpoint and also if you look at those equations. If one of the PIs is 1 and the rest of them are zeros, the numerator over the denominator is going to be 1, and you're going to have 1 equals 1 for that I and 0 equals 0 for all the other i's. Okay, so trivially, because no AJ where j is not equal to I can ever arise by item 2 up there. Hey.
I was dunking my friend on Hope Plaza for charity.
We had a Hope Plaza question a minute ago, actually. Yeah.
I was actually there.
Yeah. Okay. Did anyone come up to you and say, what are the fixed points of this?
Someone came up to me using the morphic slot, actually.
Oh, okay. Yeah. It's always hard to remember what Hope Plaza anecdotes come from what courses, but I guess that one did come from this course, right? Yeah. Excuse me. No, this is not bronchitis. This is just mop-up of the laryngitis thing I had. Were you here for the lectures when my voice was really messed up? No? Did you watch them yet? Let's not talk about it. Okay. All right, so that's one thing. That's one kind of fixed point. Now, this is the coolest thing. Another kind of fixed point is, anybody want to hazard a guess? Remember, we're talking game theory here. So what would be cool if it were fixed points of the replicator dynamics? Nash equilibria. That would be pretty cool. Okay, so more coolly, that's a word. If sigma star, comma sigma star is a Nash equilibrium of the original game, where sigma star is the mixed strategy P1 star A1 plus P2 star A2 plus up to Pn star An, then that population distribution that assigns P1 star to A1, P2 star to A2, and so on, turns out to be a fixed point of the replicator dynamics. P star equals, you can think of it as a vector if you want, P1 star, P2 star, and so on up to Pn star, is a fixed point of the replicator dynamics. Okay, now that's very cool. Now why is that the case? Let's see. Let's figure it out. So why? Alrighty, so if sigma star comma sigma star, remember Nash equilibria are strategy profiles. So don't go around saying if sigma star is a Nash equilibrium, then it's a fixed point. Say if sigma star comma sigma star is a Nash equilibrium, then sigma star is a fixed point. All right. If sigma star is a Nash equilibrium, then what do we know about Nash equilibria? We know that Nash equilibria, every action to which sigma star assigns positive probability has got to be a best reply to sigma star. So every action to which, so every action, and I'll put a sub I, to which sigma star assigns positive probability is a best reply to sigma star. And of course, sigma star itself is a best reply to sigma star. Thus, u of ai comma sigma star has got to be equal to u of sigma star for all such i's. And if you look at the replicator dynamics, what does that say? It says that the numerator of the I term fraction and the denominator of the I term fraction, when the population strategy is sigma star, are the same for all i's to which sigma star assigns positive probability. So thus, when P of t is equal to sigma star, in other words, when the population distribution of actions accords with this Nash equilibrium strategy sigma star, Pi of t plus 1 is equal to Pi of t for all I, and this is equal to Pi star for all I, for which there's too many fours in this sentence. Pi star is positive. And if Pi star is 0, that's already taken care of, because if you have Pi of t equals 0 at any t, then Pi of t plus 1 is going to be 0. So on the other hand, if it's an action to which sigma star assigns 0 probability, then Pi star is 0, and Pi of t plus 1 is equal to Pi star if Pi of t is. So if, on the other hand, Pi star equals 0, then 0 equals Pi of t plus 1 equals Pi star when Pi of t equals Pi star. Conclusion, sigma star is a fixed point. The actions to which it assigns 0 probability persist as having 0 probability assigned to them in the next population. The actions to which it assigns positive probability, because their payoffs against the population strategy are going to be the same, namely best, as sigma star is against the population strategy, persist. All right, so that's very cool. And this is probably the biggest motivator for studying these things, that a game theoretic concept, the Nash equilibrium, rises to the level of primary importance in difference equation theory, namely the fixed points of a difference equation. And when we talk about difference equations, we have fixed points, we have stable fixed points. What those are ones where if you start near them, you converge to them or stay near them. We have unstable fixed points if you start near them. And so people started going around saying, okay, well, what if the Nash equilibrium is, say, trembling hand perfect? Is it a stable fixed point? What if it's not? Is it an unstable fixed point? What if it's an ESS? What if sigma star is an ESS? Is it a stable fixed point? So all this kind of work has been going on, connecting all those equilibrium refinements to fixed point theory for difference equations. So there's lots of work, and we're not going to go over most of that. You can read about it in any of the many references I posted, connecting the stability properties of these fixed points to the equilibrium refinement ideas. For example, trembling hand perfect, ESS, etc. And that's been probably the biggest source of kind of hard mathematical results in the replicator dynamics theory. Okay. So those are things to remember. These are all salient points about the replicator dynamics I wanted to point out. Okay, now what I want to do is I want to look at these for our example games. And how many people have had a course where you talked about iterating one-dimensional difference equations, like x of t plus 1 equals g of x of t, where g is nonlinear? You must have looked at that in Strogatz's class. Period doubling and all that, yeah. So the tent shape mappings and things, yeah, all that. So you know about drawing these little pictures where you have the y equals x line and, yeah. What's that? Say that one more time. I don't even know the name of, I've never heard a name for them. Cobweb diagrams, is that? Cobwebish. Yeah, okay, well, we're going to draw some of those today. So for those of you who've never seen them before, I either apologize or tell you how cool you get to see them today, right? Whichever way you want to look at it. Okay, so let's have a look at our example games and see how the replicator dynamics idea leads essentially to what we would expect to have happen in these games. So look, before we do it, let's think about, say you're in the prisoner's dilemma. Say you have a population of players of C's and D's, right? In the prisoner's dilemma, what would be cool if the replicator dynamics did it? If you let that population evolve in time, pay off proportional cloning, and you start with some non-zero fraction of C's and non-zero fractions of D's, what do you think, what would we want to have happen to have it represent game theory? Not want in a moral sense. Vincent. Yeah, converge to a monomorphic population of D's. Okay. And say we're in the symmetrized battle of the sexes type game. We have these two pure strategy Nash equilibria where everybody plays C and everybody plays D. And then we have this mixed strategy Nash equilibrium in the middle. I mean B, not D. I always say D, I mean B. So what do you think might happen there? Just wild guess. Cameron.
We're going to convert to one of the Nash equilibrium based on the distribution of the inputs.
At the beginning, the initial distribution. Yeah, input meaning initial. Yes. It's an I word, right? Okay. Yeah, his answer was it should converge to one of the Nash equilibria based on the initial distribution of C's and B's. So, for example, if there's way more C's than B's, what do you think it's going to converge to? C. If there's way more B's than C's, B. What about if it's right near the mixed distribution? What do you think is going to happen? Depends which side it's on, meaning what? Is it ever going to converge to that mixed? Is that?
Well, no, it'll converge to one of the pure ones.
Okay, so hey, even though we know that mixed distribution is going to be a fixed point of the dynamics by this item 3 here, because it's a Nash equilibrium, right? So if you start right at there, you have to stay there. But if you're just a little bit off, are you saying it's probably going to converge to one of the ends? That's your guess?
Maybe not.
Maybe not. How many people think that's going to happen? That Paul, Kyle, why? Yeah, well, that's exactly what's going to happen. We're going to have an unstable equilibrium in the middle, meaning that if you start there, you stay there. But if you start even a little bit off of there, you're going to go away from there. And finally, the hawk dove. What do you think is going to happen there? Good question. Well, we'll see. Okay. So let's look quickly at example games. And I'm only going to look at the symmetric games that we've looked at so far. And scissors, paper, rock, you know, you're going to be sort of surprised, I think, by what happens there. Maybe not. Who knows? And for the 2 action games, for Prisoner's Dilemma, for Symmetrized Battle of the Sexes, and for Hawk Dove, I'm going to simplify the replicator dynamics to be of the form x of t plus 1 equals g of x. Okay, so for the 2 action games, note that, and so let's look at the prisoner's dilemma, for example. You're going to have P of t equals P1 of t times C plus P2 of t times D. But there's a constraint on P1 and P2. They have to add up to 1. So if you understand how P1 of t is evolving, then you can figure out how P2 of t is evolving. So if we understand the P1 of t evolution, we can figure out the P2 of t evolution easily. So let's just concentrate on the P1 of t evolution. And to simplify notation, I'm going to set x of t equal to P1 of t. So P of t itself is going to equal x of t c plus 1 minus x of t d for all t. And let's plug into the replicator dynamics equation and see how x evolves. See what x of t plus 1 is in terms of x of t. And we have a copy of the replicator dynamics east of the prime meridian and west of the international dateline, so everyone should be able to follow. So what is x of t plus 1 in terms of x of t? X of t plus 1 is equal to u of c against p of t divided by u of p of t against p of t times x of t. That's the replicator dynamics. And let's figure out what those things are. We're not going to move from equations to graphs, but I want you to see what the equations look like. So what is u of c p of t going to be? Here's the prisoner's dilemma. What is u of c against p of t when p of t is xc plus 1 minus xd? It's going to be 3x of t plus 0 times 1 minus xt. Right? Because if you place c against the mixed strategy 3c plus 1 minus, or xc plus 1 minus xd, you get 3 with probability x and 0 with probability 1 minus x. Right? And the denominator is going to be what? It's going to turn out to be a big long list of terms. Not that big, but let's do it this way. So it's going to be u of x of t c plus 1 minus x of t d against itself. So that's going to be 3x of t in the numerator. And in the denominator, you're going to have some x squareds and some 1 minus x squareds and so on. X of t squared times u of c against c is going to be 3x of t squared. X of t, 1 minus x of t, c against d is going to be 0. 1 minus x of t, d against c is going to be 5. 1 minus x of t, x of t. And the d against d is going to be 1 minus x of t quantity squared times 1. And all that has to multiply x of t. So you can see why it's nonlinear now, really graphically. And you can simplify. In any event, it comes out to x of t plus 1 is equal to some g of x of t, where g is some mapping. Okay? Or let's use a little g here. All right, now here's what the graph turns out to look like for this game. And you, if you have a graphing calculator, or how, I don't know how you guys graph stuff nowadays. One of the reasons I am tempted to take up the department's kind offer to allow me to teach ECE 2200 next spring is so that I can really learn MATLAB for the first time in my life. What do you think? Is that a worthy goal for a professor? See, the problem is MATLAB was after my time, you know, like in school. All the young guys, they had it when they were in college, they had it when they were in grad school, blah, blah, blah. It sort of came along mid-career for me. So I could kind of closet, never learn it, and, you know, that doesn't matter, right? Does it matter really, though?
Kind of crazy to me that you don't know MATLAB.
I don't know it well. Yeah.
Also, if you know the program of T84, you know.
Okay, well, that I don't satisfy the conditional of that. All right. Turns out that this is what x versus g of x looks like for this problem here. I'm going to draw this y equals x line here, and this is going to be 1. This is going to be 1. And this is the point 1, 1. It turns out it looks like this. Okay? Turns out that's what it looks like. And this is the y equals x line. So wherever the graph of g hits the y equals x line, those are going to be the fixed points, right? Because g of x equals x, that means x is a fixed point. So the fixed points are x bar equals 0 and x bar equals 1. And those are the values where g of x equals x. In other words, where the fraction of c's in the population at time t plus 1 is the same as the fraction of c's in the population at time t. And as you can see, 0 and 1 are the only fixed points. So the only fixed points of these replicator dynamics are the trivial ones, the monomorphic populations. So these are both monomorphic. So those are the kind of trivial. So these are monomorphic population distributions, both kind of trivially fixed points. But this one here, the 0C1, goes with a Nash equilibrium of the prisoner's dilemma, where everyone's playing D, Alex. This? Oh, G of x. That's supposed to be a G. Sorry. G of x. That looks worse. Would you care to draw me a nice G? Okay. G of x. Is that better? That's way better.
G of x is that C.
Yeah, and that's what it turns out to look like. Okay, so how this is what a nonlinear dynamicist would do with a picture like this, to understand where points go as time evolves. And I hope you guys can see it over here. I'm going to draw it nice and big. So here's the y equals x line. And this is one of those things, I'm not going to write down words, I'm just going to do it. And one of the advantages of video note is that, you know, you can watch this later on and hear what I'm saying, you know, if you want. So this is 1, and this is 1, and that's the y equals x line dotted in. What if I start, say, with a distribution out here where most folks are playing C, right? then what's going to be the population, what's going to be the fraction of c's at time t plus 1? Well, it's going to be whatever I get when I go up to this graph. So it's going to be this amount here, right? And that's actually lower than the one I started with. So how do I figure out what happens next? What I do is I go over to the y equals x line, and then I go back down to this curve, because this point here, this is x of 0, this is x of 1, and this is g of x of 1, which is x of 2. So this is x of 1. So as you can see, x of 0 becomes x of 1. X of 1 becomes x of 2 by going back over here, and so on, and I converge down to 0. That's a classic example of doing this thing, this business. So this is x of 3. You go up to the curve, then you go over to the y equals x line, then you go to the curve again in a vertical direction. Then you go to the y equals x line, then you go to the curve again in a vertical direction. And that's how you track your x's. And you can just, by looking at this picture, you can see that for every x of 0 except for x of 0 equals 1, x of t approaches 0 as t goes to infinity. So thus, for every initial distribution x of 0 not equal to 1, x of t approaches 0 as t goes to infinity. Conclusion, the population is asymptotically 100% d, which is what we would want, not from a social welfare moral standpoint, but from a game theoretic standpoint, to happen. Okay? Now, maybe you want to stare at this for a minute, so let's take the 2-minute break, and then we will talk about the symmetrized battle of the sexes, and we'll answer that question from earlier, and then the hawk dove. And oh, and I want to remind you guys that the folks who come in after us today, they sort of laid down the law to me last time. They said, we're having presentations on Thursday and Tuesday, so you have to get out really fast at the end of your class. So we're, if you want to come pick up homeworks or anything or talk to me, we're just going to adjourn to the little couch area outside immediately after class. Example games, other example games. So here's the symmetrized battle of the sexes. And remember, it was this one. And there was a little mistake in class last time I want to draw your attention to. It's nothing big. But I said last time that 2/3 C plus 1/3 B was a Nash equilibrium with itself. But it turns out it's 1/3 C plus 2/3 B. So CC, BB, and 1/3 C plus 2/3 B against itself are the Nash equilibrium points. And this was wrong last time. But anyway, I just wanted to draw your attention to that. Okay. So as in the prisoner's dilemma, I'm going to let P of t equal x times c. So that's the probability. X is going to be the probability you're playing C, and 1 minus x is going to be the probability you're playing B at time t. Or I shouldn't say the probability you're playing B, but the fraction of the population playing C is x. The fraction of the population playing B is 1 minus x. And if you go through this whole drill, x of t plus 1 is equal to u of c times p of t plus u of p of t times p of t times x of t. And I'm just going to figure out the numerator here. I'm not even going to bother to figure out the denominator. U of c against p of t is going to be what? I want someone to tell me what this is. So I'll put a mess in the denominator and p of t over here. And somebody tell me what U of C against P of T is in terms of X and numbers. What is the payoff to a C player against a mixed strategy that plays C with probability X and B with probability 1 minus X? Kyle.
3x of t plus 1 minus x.
Exactly. So it's going to be 3x of t plus 1 times 1 minus x of t. And I'm putting that 1 times there for the same reason you said it, just to remind you that it's the payoff to a C player against a B player is 1. Times x of t, not p of t. This should say x of t. And again, I'm going to call this g of x of t. And the mess is not too much of a mess. It's quadratic in x. No. Nothing to wring your hands about. So what does the g look like for this? You can figure this out on your whatever, TI 48? 84? See how bad I am? I've got 2048 on the brain still. It's like, okay. What? That's fair? Okay. So what does the G look like? It turns out, many details buried, that G of x versus x looks like this. I keep forgetting I want to use small g. I used big G 1 year, and I still haven't managed to rehab from that. Okay. This is 1, 1. This is 0, 0. Here's what the G looks like as it happens. Tell me what that middle point is, folks. 1/3. And it should actually, yeah. That's at 1/3. The fixed points of G, remember, are the places where G crosses, the graph of G crosses the y equals x line. What do we know from our little general discussion earlier? We know that there are some trivial fixed points, the monomorphic populations, and also any Nash equilibrium strategy, sigma star, comma sigma star being a Nash equilibrium, that sigma star has to be a fixed point. And and the fact that I have a fixed point at x equals 1/3, so here the fixed points are the all C, which is x equals 1, the all D, or all B I should say, x equals 0, and the 1/3, and the x equals 1/3, which is 1/3 C and 2/3 B. And that corresponds to the Nash equilibrium strategy, 1/3 C plus 2/3 B. Okay, so what happens if I start at some fraction of C's, which is x? If I start to the right of 1/3, I'm going to do that. And now you guys get to see one of these diagrams over here with the cobweb or whatever. So this is what it looks like. If I start at any of the fixed points, I stay there. But if I start just to the right, so this is x of 0, bigger than 1/3, I go up to the graph. Oh, I do that wrong. I was really scared for a second there. That's not what I wanted. Okay, here we go. X of 0 just a little bigger than 1/3. So this is 1/3. If this is x of 0, this is x of 1. This height here, which is the same as this one here. So this is x of 1. And then I go back to the graph, and then I go over. Then I go back to the graph, and I go over. I go back to the graph, and it's like that. And that's how I figure out where x of t goes if x of 0 was here. X of 0 gives rise to this x of 1. So I move over to the y equals x axis and I check off x of 1 down here. To figure out what x of 2 is, I have to take g of x of 1. So I go back up from the y equals x line to here. And lo and behold, this value, which is the same as this value, is x of 2. Figure out what x of 3 is. I go back up to the curve. And I don't even have to bother going back down to the x-axis. I can just stay with the y equals x line the whole time. And that's why I get this pretty little staircase. And so that means that x of t approaches what? Approaches 1 as t goes to infinity when x of 0 is even a little bit bigger than 1/3. And if x of 0 is a little less than 1/3, then boom, I go toward x equals 0. So x of t goes to 0 as t goes to infinity when x of 0 is less than 1/3. So, just as Max conjectured a little while ago, if you start with even a little bit of a plurality of C players in the population, this replicator dynamic payoff proportional cloning thing is going to cause you to converge on everybody wanting to go to C, playing C. If you start with even a little bit fewer than 1/3 B players in the population, then, or fewer than 1/3 C players in the population, then you're going to head for everybody playing B. Okay? Everybody got that? All right. And finally, I want to look at Hawk-Dove. And this is the only game where you have to do that add a positive constant at the beginning to make sure all the payoffs are positive. So I'll show you the way I do that. So as for Hawk-Dove, the original game is this. And to do the replicator dynamics in discrete time, what we need to do is add a positive constant. So I'm just going to add 26 to every payoff to make them all positive. And I get this modified version of Hawk-Dove where you have 1, 1, 76, 0, 0, 76, and 41, 41. I like that 41 there because it's prime. But the point is that this game has exactly the same Nash equilibria, namely h comma d and d comma h and 7/12 h plus 5/12 z against itself as the original one. You can figure that out. Adding a positive constant, 26 is here. Sorry. Thank you for not telling me. Yeah, so adding a single positive constant to every single payoff in the game does not change the Nash equilibria of the game because it doesn't change the notion of what's a best reply to what. If you get a bigger payoff when you play this against that strategy and you add a positive constant to all the payoff, that's still going to be the case. So that's why the Nash equilibria stay the same. And you can go through this drill and find the G. So again, you let P of t equal x of t h plus 1 minus x of t d, and you find x of t plus 1 is equal to g of x of t as before. I'm not going to write down any equations for that. We've had enough of that for today. And this is what g looks like. Draw on the y equals x line. What's that? Oh, thank you. Thank you. Thank you. Aversion therapy is what I need, I think. Okay, so if this is 1, and this is 1, this is 1, 1, and this is 7/12. It's going to look like this. Whatever the opposite of that one was. This is what the G looks like. Okay, so again, you have 3 fixed points, just as you had for the symmetrized battle of the sexes. X equals 1, x equals 0, and x equals 7/12 are fixed. So what does x equal 1 correspond to in population terms? It responds to everybody's a hawk. X equals 0 in population terms corresponds to everybody's a dove. Unlike the battle of the sexes and unlike the prisoner's dilemma, those populations don't go with Nash equilibria of the original hawk-dove game. H comma H is not a Nash equilibrium. D comma D is not a Nash equilibrium. This one does. So these don't correspond with Nash equilibria because this is the all H population. This is the all D population. But this one obviously does, because 7/12 H plus 5/12 D is an equilibrium against itself. So what happens with this guy? With the cobweb or whatever diagram? Let's see. Let's draw it big enough. It's more like DNA.
It looks like DNA. It kind of looks like DNA.
Oh yeah, twisted double helix kind of thing. Yeah. I had this teacher who was really good at drawing 3D looking double helix on the board.
Drawing 3D is pretty tough.
Yeah, I don't know. She was really good at that. A very odd person, I must say. Okay, so you can actually prove that this slope is positive. Anyway. Okay, so what if I start at the all hawk population or at the all dove population or at the 7/12 population? I stay there. What if I start a little off from one of those? So this is 7/12. Say x of 0 is over here. Say I've got lots of doves in the population relative to hawks. Then the hawks are going to proliferate in some, you'd think, right? Because they have a huge payoff against doves. Much bigger than the doves do against themselves. And sure enough, that's what happens. So if x of 0 is here, then x of 1 is here, x of 2 is here, this is x of 1, this is x of 2, and so on, x of 3, and it goes on and on, and boom, it approaches the fraction 7/12. If I start with x of 0 over here, go up to the curve, it goes just the same way except down to 7/12. X of t approaches 7/12 as t goes to infinity for all x of 0 not equal to 0 and 1, 0 or 1. So in the hawk-dove population, your populations actually can converge to a stable distribution of 7/12 hawks plus 5/12 doves under these replicator dynamics. All right, so general comments about these 3 examples. In dynamical systems theory language, and when you look around a faculty and you say, who knows what, like what's your core expertise or whatever, like that's mine. It's dynamical systems theory, okay, versus anything else. If you want to, like I know it a lot better than I know digital communications, MATLAB, all that kind of stuff. But anyway, Drew, yeah.
Is it always true that the fixed points are going to
No, they're going to be okay. Here's an example of another one. Like if you have more than say 2 actions, if you have like 10 actions, then all the populations that have say only actions 1 through 5 represented and not actions 6 through 10, any such population, that's going to be an invariant property of a population, to have no representatives of 6 through 10. And if you look at the game that pits those first 5 actions against just themselves, with ignoring the existence of the other actions, the Nash equilibria of that sort of embedded game are all going to be fixed points of the replicator dynamics. So basically, you're talking about a simplex, that's the set of all strategies, and on the faces are going to be invariant, the faces of all dimensions. It's hard to think above 4 dimensions, but if you have like 10 strategies, it turns out you have a 9-dimensional simplex. Every face of dimension 8, every face of dimension 7, blah, 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 down to the faces of dimension 0, which are the extreme points. All those are invariant sets. And in those sets, in general, you're going to have fixed points. And you can characterize those fixed points as Nash equilibria of embedded games, but they're not Nash equilibria of the whole game. Okay, but that's a very good question. And I really wanted to make a couple comments about stability, instability, but we have to get out of here right now because those really nervous people from the next class are going to come in and want to do their presentations.